Hello there, welcome back to Petrophysics Rocks. I had the opportunity the other day to sit down with Henua at the Aberdeen Formation Evaluation Society. We did a podcast, one of their Logs Have Voices series. It was an enjoyable chat. It's only about half an hour long, which is a bit shorter than most of my videos on here. So I'll leave a link to that in the description below. We discussed a life in petrophysics, a career in petrophysics, and what geoscientists, new geoscientists and engineers could expect from their petrophysicists, or if they indeed wanted to dabble in the dark arts themselves, what they could expect from a life in and amongst the squiggles. But during that conversation, she asked me what my definition of petrophysics was. And I heard a good one recently that was the petrophysics is the art of turning reservoirs into spreadsheets. And I've done that quite literally in this presentation, actually. So I'm wanting to introduce to you the Drillulator, which is a petrophysical simulation model that I've built in Excel to mimic a reservoir that we can drill wells into and run experiments on. And I've used that in this presentation to try and address some of the concerns that I often hear from people like my good friend Mark Bentley, who often says that the chances of well data matching the model data, matching reality, are vanishingly small. And so I've hopefully addressed some of those issues in this presentation. And also my friend Mike Cooper at Trove Energy, he also called me out on my last presentation, the sums and averages presentation, for not using relevant wells for my Hutton example. And I did that on purpose, just to illustrate a point and fall into my own trap there. But hopefully I've addressed that in the comments to the last email, to the last YouTube video, and also here in this presentation. I would encourage you to make comments and interact down below. It's all good for the algorithm, and if you like this kind of thing, then please do press the like and subscribe down below. It really helps. We've got about 400 subscribers now. It would be nice to get to 500, maybe 1,000 at some point. I'm sure there are enough squiggly lying guys out there, people interested to get us up to that level. That would be great. And in the meantime, I'm going to leave you with this presentation now. Reservoir depth trends, as I say, it's the latest one in my Petrophysical tips series. If you can like and subscribe and comment down below, it would be much appreciated. Okay, cheers, thanks a lot. Hello there, welcome back to Petrophysics Rocks. This presentation is a follow-on to my last one on sums and averages. I was called out by my colleague and friend Mike Cooper at Trove Energy for selecting wells that weren't necessarily relevant to the Hutton structure. And obviously I kind of pointed out to him in the comments that was a bit deliberate on my part. I deliberately chose some wells and then fell into my own trap so that I could demonstrate the issue about applying sums and averages to predict the properties of the fields that we're hoping to discover. And I'll mention that a little bit more in this presentation, and I go into a bit more detail about that. And also some other things that came to mind were my other colleague and friend Mark Bentley at Trax Training. He always used to say to me that the chances of the model matching the wells and matching the reality, the subsurface reality, were all vanishingly small. And he always used to chastise me for believing in the wells too much when you're constructing 3D models. Now, I may not disagree with him in general, but I do think that the well data can tell you something interesting about the wells, and maybe we can push it a little bit further by using things like confidence in the mean. We may not know the exact answer early on in the field's life or the field appraisal phase, but I think quite early on we can get a good sense of the range that we can have confidence in, even if we don't know the actual final average answer. And the other thing I'm going to introduce here is the Drillulator. I made a presentation a while ago with my Trouble with Rocks presentation on the Conglomerator, where I used an Excel tool to sort of predict average rock properties for conglomerate reservoirs. And at the time I took that further a little bit to a thing I called the Drillulator, which was an Excel model which we can drill a number of wells on and see how many wells we need to drill to be confident in our averages. So I'll take you through that as well, and I'm also going to ignore a bit of advice that Mike Cooper gave me. He said, don't go into all that Excel nonsense. Nobody's interested in that these days with all this Python stuff going around. But nevertheless, if you make it long enough, I'll take you into the workings of the Drillulator beast, just so that you can see what's going on. I'm probably not going to release it. I'll give you a free copy of it because it's a complicated thing, and I don't want to be answering too many questions. I may make up a version for release, but I haven't quite decided yet whether I'm going to give it to you. But I'll show you the bones of it, and then if you're that motivated, maybe you could give you some ideas about constructing stuff for your own spreadsheet. Okay, I've been dribbling on a little bit now. Let's go and have a look at what this presentation is going to be about. It's mainly about the reservoir depths, and it's going to follow on, as I say, from the previous presentation I made. I'm going to skip all the biography stuff, and we'll just probably go back with a quick refresher as to where Hutton is, and we're going to use that field again, and then we're going to talk about depth trends in particular, and the issues that I've encountered in my career trying to convince people about depth trends. And there are various competing tensions, if you like, as to why people don't like to believe me sometimes. And then I'll show you, as I say, the Drillulator, the Excel spreadsheet module where we can drill pseudo wells into pseudo models and come up with pseudo averages. And then I'll finish off with some conclusions. Okay, so we'll just go back to the UK. Remember where we are, just as a refresher. We're in the UK, the northern North Sea, and here is the Hutton field up just north of Shetland, as we were before, and here it is in the B.R.E.N.T province, famous B.R.E.N.T North Sea oil field, and we have a similar reservoir here in Hutton. This is the TLP. The tension leg platform that was over producing from Hutton until about 2001, 2003 was it? I can't quite remember, before it was removed. But anyway, as I say, we're interested in the subsurface stuff. This was the first development well. And in the last presentation, we went through and discussed how we analysed the B.R.E.N.T reservoir, the Broom, the Rannoch, the Etive and the Ness and the Tarbot layers in here, and then we can take the sums and averages on the bottom and process those sums and averages to give us a feel for what the average properties of our hope for discovery field was going to be. So this was the B.R.E.N.T zone that we looked at, which is the whole interval, which we looked at in the last presentation. Okay, so remember we had 10 appraisal wells at first, and I made some assumptions. I said, what can we tell from these 10 appraisal wells, if you like, reliving the field's development? So from these 10 appraisal wells, which, as Mike points out, aren't all necessarily relevant to the Hutton field itself, but one of the issues is that when you're dealing with management in particular, they want you to use all of the data, tend to. So if you have that data available early on in a field's life, it's very tempting to use it all. And there are things in here, obviously, that are providing their valid samples of the geology of the interval, the B.R.E.N.T, things like net to gross, when the thing was originally laid down in geological history. You know, the controls that were on the sand shale ratios of a particular field, they probably don't depend too much on depth, but they're just samples of the geology, and if the geology can do this thing in one place, if you're in an interchannel area and you get slightly less sands, or if you're in a channel axis you get more sand. And so sampling that geology is probably just a reasonable thing to want to do. But as I say, later on I showed you that we had 21 wells, and then by the time the field was developed at the end we had up to H45 with the original wells. So we had like 64 appraisal wells on the appraisal and development wells. And so what I did in my last presentation, I said, well, okay, now we know the answer at the end of field life. You know, how good were we at the beginning by using this limited data set to predict the reservoir properties? And as I've already said, that was a point of the last presentation. And we discussed things like confidence in the mean. You know, how confident are we that our average field average porosity was, for example, was going to end up here within these limits? What's the 80% confidence level that we're going to have a final field average represented in this data, that we know the answer at the end, sort of stuff. So anyway, and the other thing that I mentioned at the time in the last presentation was this use of looking at things graphically. Don't just look at tables of numbers. Have a look at them in XY space, or YZ space in my world or whatever, but try and have a look at them graphically. Have a look for outliers. What's going on with these two wells, for example? Now, I happen to know that those two wells encountered the Brent interval in some higher fault blocks, different fault blocks, and they weren't complete reservoir sections, and so they were re-drilled into the main reservoir. So it's those sorts of observations that you make. How relevant are these wells? And any outliers, have a look at them, investigate them. Are they representative? Is there some special feature about them? But here you can generally see there's a nice a depth trend here, and if we look at that closely, swap the axes around and whatever. So we've got to match my upcoming cross plots. We've got a porosity trend here that is actually decreasing with depth. I apologize for flipping the axes on you, but you'll see why later. So what I want to do is, for now, let's just take that 21% porosity on average, and we'll just file that away for now, and we'll come back to that later. So that's the average field properties from those B.R.E.N.T zone averages. And obviously, when you first got the first couple of wells, as I said, there's a natural tendency to use all the data that you have, and also management particularly are very wary, and geologically you'll be very wary of narrowing the ranges. You'll come under pressure to keep the ranges as wide as possible at this early stage. We never know what we're going to encounter. So although it may be true that we should really be using this kind of narrower range with a depth trend, there are pressures on us to keep the range as wide as possible, and also a lot of these simple Excel spreadsheets and Monte Carlo work just put the population in. Products like REP, which of Monte Carlo, proper software for reserves estimations, they do allow you to put depth trends in, and therefore you can put depth trends and standard deviations in of the data, and that's a very useful thing to do. But again, just have a look at the data here. This is one of those wells that I told you about, partial penetration, not particularly representative. But have a look at the data graphically. See does it make sense to use it, and then you decide. You and your managers decide what's representative and what's not. But okay, so if we often have a look at this data, everybody's reasonably comfortable with this as a depth trend. You know, these are the average well data we got here. There are all the 64 wells there, but one of the things that people get less comfortable with is when I stick up a log plot here with all the data in. Now this is all the data from all 65 wells at half-foot log increment. So that's 49,800, 50,000 data points, which at half-foot sampling is representative of 25,000 feet of log data. and I've just coloured it in by well. The blue wells are the first appraisal wells. The green wells are those first 10 platform pre-drill wells you see over the full depth range, and then these red wells are the 65 wells, sorry, the 45 wells that were drilled as development wells on the Hutton field, and they're actually over a bit of a narrower depth range, which what gave rise to the issues that I was having with trying to predict what the final average Hutton field porosity was going to be, because obviously it doesn't quite have this low porosity, deeper stuff. But oftentimes I found throughout my career that when I put up a log plot like this, everybody, geologists in particular and management, throw up their hands and they say, oh my gosh, look at that spread, how only a petrophysicist would put a line through that data. If we go back again to this is the well average data, and what you'll see is I've kept these trend lines, these bounding surfaces lines, and I've put them in white on these cross plots here just to say where the final well averages appeared. And when you put up log data, often at half-foot depth increment, there's a bigger cloud, and people don't like it. But this is still a mathematical fit through here. It's a free y on x regression, and the math is mathing properly. And this is a mathematical fit to this data, so there is a trend in there that's mathematically defined, but people look at the spread and they don't like it. The other thing, of course, is that this is the gross interval. This is all the wells and all the data, including the non-net. So this is the total porosity, phi t, throughout all the log measurements here, and this is the half-foot log measurements that you're averaging up for all 64 wells. So if we have a look at this color, I can color it up by zone. So the blue is the Tarbert, the green is the Ness. If I just toggle between the two, you'll see the zonation colored. Now an issue here is that actually it looks like the broom is the most significant, but that's only just because it's plotting over the top here. That's the last zone plotted, so it looks like it's dominating. If I split this out by well, you'd see that actually there is pretty even coverage, but more of that later. We can also color the points by V clay here. So this is the shale volume. Here is the nice clean sands, the yellow ones, and here are the shales in dark brown. These V shale up to over 50%. So one of the things we can do is let's just get rid of the shales for now. We're not that interested in the shales, so we're just going to look at the sand. So all I'm doing is I'm just going to take out the shales, and you can see immediately that the average shifts up. The average porosity of the stuff that's remaining increases, obviously, as we've got rid of all that shale, which does have a total porosity. It has a certain water content, but let's take that out. And then what we should do is just take all the net reservoir qualities, so everything that satisfies our reservoir criteria, and I've arbitrarily determined that everything that's over 1 millidarcy permeability is remaining. So basically, this stuff here at lower porosities is generally less than 1 millidarcy porosity, 1 millidarcy permeability, which is a typical net cutoff for oil sands in the industry. We generally say that if everything is less than 1 millidarcy permeability, it won't flow oil, and if it's less than 0.1 millidarcy, it won't flow gas. Now that's a generalization, a rule of thumb, and ultimately you would need the reservoir simulation to demonstrate that actually that rock is not flowing, and in fact it may flow slightly, but traditionally we use a 1 millidarcy cutoff, and so let's just cut that out. So we cut all the best. We cut all the non-net reservoir out. So this is the reservoir quality sands. And now you can see it's starting to match my well averages here, but this is still log sampled data. This is sampled at half-foot increment over everything, and we're down to 32,000 points now. So if you look at 32,000 over the original, what was it, 64? So that's around about 50%. 50% of the points are net, and 64% we've cut out now as as non-net. So without getting into an argument here, this is the total porosity. I'm just going to show you what the effective porosity is. So if you like, that's clay correcting. Now, I don't want to get into a discussion or argument about the difference between phi T and phi E. That's probably the subject of another video. But here you can see the phi E, and if you notice that it's mainly this poorer quality rock here that moves the most. Oops, excuse me. So that's the phi T, and that's the phi E. You're basically saying this stuff here has a higher clay content, and therefore the water, the porosity associated with that is not necessarily effective. So you remove that from the equation, and it drops down the poorer quality interval. Whereas if you look at if you keep your eye on this in this sand stuff here, the sand, the yellow clean sand, doesn't move that much. Okay, so that's it's mainly this phi T to phi E correction is mainly affecting the poorer quality rock. I'll say no more about that for now, but that, as I say, I may do another video on that whole thorny bag of worms. Anyway, so this is the phi E, and that's the whole interval at half foot log increment. Now, if we take a look at upscaling it slightly, let's have a look at this. Is now upscaled to the what I call the bed thicknesses. So this is any contiguous interval of net sand. If I toggle between the two, this is any contiguous net sand. You see it's slightly upscaled. These are down to 3 foot, maybe down to 1 or 2 feet, but any continuous bed of sand, I've upscaled it from this half foot increment, and you can see that the range of P90 to P10 does increase, and this is the whole idea of, you'll often hear mentioned, regressing to the mean. So what we're doing is we're regressing to the mean as we upscale. So if we go from these net bed thicknesses, we upscale to this zonal interval here, this layer interval. So this is so we'll just have a look at this layered interval here. So now we're upscaling by these reservoir sublayers, and then if we upscale again to the B.R.E.N.T zones, the Broom, Rannoch, Etive, Ness, and Tarbert, you see each time we upscale, we're regressing to the mean. The spread is getting less and less, and still you can see it's starting now to match the zonal averages that we make. And if we upscale by well, so each one of these lines now is a well with a bit of Ness, Etive, and Rannoch in it. This one's got a bit of Tarbert at the top. You can see each line is a well. I've still got 32,000 data points in here. It's just that they're all plotting over each other. And you can see now that actually this well average here is slightly less spread than my original well sums averages. Maybe there we can review that, work out what's going on. And if you look at the layer average, obviously, if we take the average, I know this is the middle Ness, for example. So this is the middle Ness in the Hutton field. The average porosity there is, what is that, 15 PU. And all the other zones here, the Etive is the best zone, then the Rannoch, and then the Broom. And surprisingly to me, actually, that some of these Ness intervals on average, the upper and lower Ness, are slightly lower porosity. Again, I apologize for the reverse scale on here or whatever, but you can see the average per zone, per field is one number, so it's a constant number, so we don't have the depth trend in it. And if we take the average field porosity, overall 34,000 net data points, that's the average field porosity. And if we have a look, what does that say? It says we're at 20.9 PU. This is fractional here, so this is nearly 21 PU is the average porosity. And if you recall, if we take out, we go back to our envelope here, we take the average porosity from our zonal sums and averages. We got 21.2, so 0.3 of a difference, 0.4 of a difference to the zonal averages, which is close enough. I hope you agree. So within half a PU. So what can we do with this? And this is where I wanted to sort of take this now. You saw how the scatter reduced as we upscaled, as you'd expect. So how can we use this? And this is where I'm going to introduce this Drillulator. But let's have a look at the subzones in particular. So here is those, going back to these B.R.E.N.T subzones here. So this is the average properties for each of the Broom, Rannoch, Etive, Ness and Tarbert. One of the things that I'm going to give you a little bit of a sneak preview of my Drillulator as it was back in 2019 here. I've got 5 zones or so. Oh, what's that? 5 zones. I was going to use, this is my old Drillulator from 2019. I was working on a West African field here, and you can see this is an Excel spreadsheet with various layers on it. And I had the 7 layers in here, 7 or 8 layers, and I thought, well, okay, I could take this data, as zonal data, and I could just put it into my Drillulator, and I could create an Excel model with these 6 or 7 B.R.E.N.T layers, and use the variance in the B.R.E.N.T layer as the zonal upscaling within this model. Okay, but more of that later. You'll see for various reasons I've gone a bit overboard on my final Drillulator. So anyway, so what I wanted to do was go into now if I take these B.R.E.N.T zones and I just color them up by the reservoir layers. If you see that, so if I toggle between the two, these are the B.R.E.N.T zones, and if I color them up by the reservoir layers, and then what I want to do is I want to use that same color scheme, and then I'll go back to the bed data, because I noticed that when I went from my 7-layer Drillulator model, I went to a 100-layer Drillulator model, and therefore that meant that my average layer thickness went to around about 3 foot thick, because on average the B.R.E.N.T reservoir is around about, the net B.R.E.N.T reservoir is around about 300 foot thick on average. So if I make a Drillulator at 100-layer thickness, then that's 3 foot layers each. So I decided I wanted to make something with a variance on a 3 foot scale, and again we'll cover that again when I introduce the Drillulator. So here's the data at 3 foot variance, and then what you can do is you can take that data, contour it up so you see where the frequency of the data points are, and then I do a box and whiskers plot here. So at each depth bin, here is the average. This tick in the middle is the average, and you can see that the regression is basically going through the mean of these data points, and the box represents a standard deviation. So the line can appear anywhere within that standard deviation, and then for each bin there's a min and max data set within each bin, and so therefore I can take that data and I can capture the statistics of those bins in an Excel spreadsheet. And so here is that's the whole of the B.R.E.N.T interval, and on average the net to gross, what was that? Did I say that? Yeah. So the average of the net to gross the average net to gross was 63%. So there's 32,000 data points, and obviously there was so 63% net to gross for the B.R.E.N.T as a whole. That's all the zones. But if we just look at the Tarbert, now that's actually only 3% of the net reservoir here. We come up with a similar set of statistics, and a slightly higher net to gross, 83% net to gross in the Tarbert. The upper Ness is a bit more, 50%, 55% net to gross. We can see a few more data points. It forms 18% of the B.R.E.N.T. The middle Ness only has 1% of the net B.R.E.N.T reservoir in here. That is that 15 PU again. So that's a poorer quality rock, and it's much lower net to gross, only 6% net to gross. 1% of the Brent reservoir. The lower Ness, again, we can see these trends are all fairly similar, and the stats are there. Again, similar net to gross, 55%, net to gross, 22% of the reservoir. So we go through the ETIV, the RANEC, the B.R.E.N.T, and therefore we gather the statistics and we can summarize them all at these are the basic proportions, the net reservoir proportions of the Brent reservoir, and I've got those these equations that describe the porosity depth trends. So then let's go into the Drillulator itself. I've already hinted this is the 2019 Drillulator, my West African one, and what I've got is I've got 200 columns, so it's 200 columns wide and 27 rows in this case. That's 5,500 cells. And along the x-axis, along the top here, this is the crestal depth. So from crest to flank, that's the top surface depth, if you like. And on the y-axis, I've got a thickness, reservoir thickness. So at any point, the depth of this cell is basically the crestal depth plus the cumulative thickness of the reservoir here. So that was what I was doing in 2019, and I thought I could use that to calculate my zonal properties. But to make it easier for myself, actually, I decided to create a 100 layer thick Drillulator. And what that does actually is it allows me to say, right, okay, well, if I've got 100 layers and the RANEC is 15%, then I can use 15 layers for the RANEC, 13 layers for the B.R.E.N.T, 28 layers for the ETIV, and I rounded that up to 1 layer for the middle Ness. So you can see that's what this proportions are here. So the Tarbet here, if I zoom in, the Tarbet, the Ness, and the middle Ness, those layers are proportional, and I thought that was a quicker way of doing it. I can actually introduce a grid of net to gross to do that, but for the purposes of this, I've just layer proportioned the thickness from the Brent zones themselves, and the porosities come from this equation. Let me just zoom in here. So I've got those equations, the gradient intercept and a porosity at the crest, and so to calculate the porosity in each cell, I basically use this zonal equation, and over this interval here, you see the Tarbet is 3% of the reservoir, so it's 3 layers. Middle Ness is 1%, as I've already explained, and therefore I calculate the porosity in each cell based on these equations, and then if I want to change the layer thickness or put the crestal, I've said it's 9,200, and it goes down here, goes down to 10,900, and then what we do here is I can sample the model with the wells. So basically I drill some wells in the model at various stages, and then I report the average properties of that line of cells up here as my average well properties. And so therefore I can evaluate the well properties and the whole model properties. Obviously I know the average properties of the whole thing, and then I can sample the well population as well. So in this wells I've got 30 wells put into the Drillulator, and in this particular case the average model properties are 21.23%, and the average properties of all 30 wells are 21.2%. And here you can see the histograms of the model porosity and the histograms of the well porosity, yeah. And these are the relationships that I've used. You see with the porosity depth again to match, I've got the depth increasing along the x-axis and then the porosity decreasing along the y-axis. Please, I do apologize for confusing you with a strange choice of directions. And then one of the other things that we can do is, obviously the main thing is to sort of look at the order in which you drill these wells. So what I've done here is I've put a drilling order in here. So I've said that the crestal wells are 1 to 10, The mid-flank wells are 10 to 20, and the distal wells down flank are 20 to 30. And then I've basically put the well order in here, such that I've simulated a development. So the first few wells I drill up at the crest, as you might well do, to get the oil out first, and then you might want to drill a couple of down dip injectors to get some pressure support. You may have a semi-sub campaign if they're subsea wells, so you bring on a semi-sub, drill some subsea injection wells. You're likely to do 1 or 2 down there or whatever. This is just a notional kind of realistic. Well, then you might want to do some infill wells in the mid-flank. This is the axis here, so this is the well number on this axis, and then you can drill some more down dip wells and some crestal wells or whatever, and then you look at that. So that's a notional field development plan, and then you kind of say, well, where do we start to get how many wells do we have to drill before our running average porosity, which is this magenta curve here, gets to match the field average properties. So in this particular realization, you've got up to 23 wells. You've got to drill 23 wells before your well averages start to match your field averages. So that's quite a few. But remember from the last presentation, quite early on, you can have confidence in the mean. We're pretty confident this is the range, these red lines, this is the range that that we're confident that the final average is going to end up being between, sort of stuff. This is the 80% confidence level. So there's a P90 and a P10 range quite early on. Now, you'll notice that early on here, when we're just drilling wells at the crest, then we're biased. We don't know any difference. But as soon as we drill a down dip well or a well in another location, then the variance crops up, and then the maths takes care of it and says, actually, okay, well, I'm fairly confident, even though I've only got 6 or 7 wells, that the range should be within the confidence range should be between these two levels, even though we've only got a limited number of wells. And you'll see here that the confidence in the mean is stable quite early on in the process after only 6 or 7 wells. And so the next thing I wanted to do, so that's how this spreadsheet is set up. We'll do this. We'll add some noise. We'll add the noise in, and I'll show you how to do that when I show you the spreadsheet or whatever. So let's add some noise. So what I've done there is I've used the Excel random noise generator, and what I'm doing is I'm taking the variance by zone. So those equations plus this noise feature. So that's no noise, and that's the noise, the variance by zone. So each of these wells, here's 3 example wells. There's the down flank well, the mid flank well, and a crestal well. Just some example traces there. So you can see this is the well traces here, and you can see that the average porosity is varying by zone. And so if I run through a few realizations, you can see that by pressing F9, the refresh button, I get random noise, and each one of these zones, for each column, if you like, each well is only varying by the zonal noise. And you can see in this particular case that, again, still the confidence is pretty stable. The average is moving around a little bit. So that particular example there, I'm not confident in my average until I got way up to 29 wells, remember. So that's one thing. And then let's have a look at the bed thickness. Okay, so this is Drillulator by zone, but if we look at the bed average, now the variance is by bed. Remember that this is still 3 foot thick. So now let's vary each individual bed, and obviously you go from the zonal averages. All these zones are changing the same, and we put the bed average in. So this the nature of this spread increases slightly, as we saw before, and now obviously each bed is independently allowed to vary by the variance of the bed. And here I was looking to see whether that makes a difference. It does make a difference on the well porosity depth trend. For those wells can kind of regress to the mean a little bit more easily. But here the averages, again, if I run various realizations, can vary quite a bit. In this particular realization, it's 18 wells. So then I thought, well, okay, obviously this well order is just one realization. What if I reversed it? You see, at the beginning, you're drilling wells at the crest, so therefore you're biased towards the crestal. You're above the field average, and if you reversed it, if you drilled your injectors first, you'd be drilling and you'd be below the field average, as you'd expect. Again, still, the confidence in the mean is still, providing you've drilled a couple of the environments, the confidence in the mean is quite stable, but you're not reaching an average until 17 or 18 wells. So I have a few realizations of that. And again, the average. Now, let's just go random now. So let's just say, well, okay, there's no drilling order imposed. We're just gonna drill the well spat randomly up on a 5-spot pattern, like they might do in Alaska, for example, and then just do various realizations. And that probably does a little bit better, actually, in terms of the average stability, because randomly you're going to drill, sample the population by a random means, and here the stability of the average is a bit better, actually. Okay, so anyway, at the end of this, if we go back, so we've got the average model property of 21.22 and the average well population property of 21.11, and if we remember, we put that number in our envelope, and we go back and check that. So that was the average of the well averages, the real well averages, and this is the average of our model and our Drillulator. So 21.22, 21.2. So that all kind of hangs together. So it's an interesting game to play. What I was trying to do was to prove Mark Bentley wrong, and see how many wells do we need to find out the average properties. And it looks like he might have been right, eh? It's vanishingly small to get the average exactly right. But I would still contend, based on my last presentation and this one as well, that this confidence is stable at quite an early wells. Now here, I was going to ignore Mike Cooper's advice and just go into the Excel spreadsheet here, just to give you an idea of how it's kind of structured. And let me just view, put a new window in. Then I'm gonna view, arrange it all, make it tiled. Don't you worry, this is a depth thing, but let's go down here to the main Drillulator, and here's the well population. So I've got both of them there showed. So here's the layer thickness. So 3-foot layers, and then we're plotting from 9200 down to 10900. And you can see here that data. I've left it as randomized data. Let me just press F9 to play. So why? Okay, it's moving. Oh, some delay in this. So why aren't those averages changing? Seem to be stuck. There we go. F9. So you can see that this is changing slightly. It's not a great demonstration after all. So Mike was right. Let me just. So what I've got here is I've got some averages. Here was the random averages. Here's if I just I put some random numbers in here, and then I can data sort by column A, and then I can put the random copy, paste special values in there. There's just some random noise. Press F9. Oh, so this one starts out, you see, at quite a high well. So that's an injection well deep down flank, which is why the averages are starting out lower. Anyway, so that's that. The noise, if you like, is I've got a separate tab, and I've got using the norm dist function. I basically created some noise for each of my reservoir layers, and what I've got here is I've got different noise levels depending on whether I'm doing zonal noise or the bed noise, or indeed switching off the noise. So I press no, I don't want to have the noise there, and then you can see those are the different equations that we've got. Okay, so never demonstrate, so Mike was right, but I just thought that would give you an idea of how it looks up. Basically, you basically do a lookup function. You calculate your depth in each cell, calculate this equation, and add this bit of noise in if you've selected it. Okay, so that was Drillulator. Let me go back to the presentation if I can, and wrap up with some conclusions. So, property depth trends, petrophysics conclusions. Get there in the end. I would say that the top tips are that depth trends are often real, despite the cloud and the spread that often puts managers and a lot of people off. You think, we can't draw a line through that, but underneath, the maths is the maths, and providing you are thinking about it and go through the various upscaling steps, you can use the appropriate spread for the zone type, if you like, that you're trying to estimate, and you can use these depth trends, as I said on my previous presentation, to look at the data, to QC it. Check out those outliers. Why are they there? Are they there for a valid geological reason, or is it just some calculation artifact? The confidence in the mean is pretty typically effective from 5 or 6 wells onwards, I would say. So once a petrophysicist's got 5 or 6 wells in a region, in an area, and there's no obvious reason to discount one of them for not being representative, then I would say that you can be pretty confident that you can use the confidence in the mean approach to predict a range of viable outcomes, providing you have, as I say, 1 or 2 wells that sample the whole depth or geological range. But the actual field average may not be apparent until you got up to around about 20 wells, so perhaps Mark Bentley was right after all. Okay, so that's me finished eventually. I'm sorry about the presentation, but I just hopefully, sorry about the demonstration of the Excel spreadsheet. I just thought it was valuable just to sort of go in there and give you some ideas about how you might structure a spreadsheet. As I say, if you've made it this far, I might give you a copy of it if you want to send me an email. But for those who ducked out early and didn't put themselves through this, we'll leave it, as I said, as a potential future deliverable from me. Okay, thanks a lot for your attention. Much appreciated. See you next time.